Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the pipe flow systems and we were discussing about the pipe networks. With respect to a typical example, we have seen how to derive the equations, energy equations and then the mass balance or continuity balance equations for a typical case, and then we are discussing about the generalized form of these equations. So, today further we will see how these equations, the generalized equations can be written with respect to the continuity balance equations and then the energy balance equations, and then how we can solve these equations with respect to linearization or with respect to successive approximations, and then we will further discuss various types of pipe flow analysis of pipe flow solution. So, the pipe networks which we have seen, say we have seen that there will be number of loops, and then there can be, say we have to, most of the time we have to assume the flow direction and then flow through each pipe. So, this aspect we have seen, and so with respect to this, what we have discussed in the last lecture, the generalized network equation, the continuity equation at a jth interior node, we can write as sigma plus or minus j qj minus qe is equal to 0 as in this equation, where j refers to pipe connected to a node and QE is the external demand, and this here we use the positive sign for flow into the junction and negative sign for flow out of the junction. And then as we discussed in the last lecture, the energy balance around an interior loop can be written as sigma plus or minus I W I is equal to 0 as in this equation. Positive is used for clockwise and negative is used for anti-clockwise. So, here I pertains to pipe that make the loop. So, these are the two general form of the equation. One is the continuity equation and another one is the energy balance equation. And then this energy balance along a unique path, we have seen that there is a possibility of a pseudo loop with respect to the fixed grade nodes. With respect to the reservoirs, we can have the pseudo loop that we have seen in the last example. So, with respect to pseudo loop connecting two fixed grade nodes, we can write sigma plus or minus I W I minus H P I plus delta H is equal to 0, where this H P is the head across the pump and delta H is the difference in magnitude of two fixed grade nodes in the path ordered in a clockwise fashion across the imaginary pipe in the loop. So, this equation details also we have seen in the last lecture. So, now if f is the number of fixed grade nodes, there will be f minus 1 number of unique path equations. So, as we have seen the last time, say the last example which we discussed, there were two reservoirs. So, there will be we can have one unique path, or depending upon number of fixed grade nodes, there will be f minus 1 number of unique path equations, and if there are p numbers of pipe elements in the network and j numbers of interior nodes and l numbers of loops, then we will say that the pipe is properly defined, the pipe network is properly defined when p is equal to j plus l plus f minus 1 as in given this equation. So, where p is the number of pipe elements, j is the number of interior nodes, l is number of loops, and f is the number of fixed grade nodes. So, now say for example, if you consider the last example which we discussed earlier. So, with respect to this example, here we can see that say there are 7 pipes, 2 reservoirs, and we have seen there are 2 loops. So, with respect to this example, we can say that this pipe network is defined properly when this here with respect to this equation, and that means p is equal to j plus l plus f minus 1. So, here for this pipe network which we have seen, we have j is equal to 4, number of interior nodes 4, l is equal to 2, and the number of loops 2, and f is equal to 2. So, p is equal to j plus l plus f minus 1. So, that is equal to 7. So, that pipe network which we have seen, we can say that it is properly defined, and we can get a solution by using the generalized equations which we have discussed now. So, now the additional necessary formulation required is the relation between the discharge and loss So, as we derived earlier, we can write this W is equal to R into q to the power beta plus sigma k by 2 g a square q square. So, here this minor loss we can say generally this beta is equal to 2. So, minor loss in terms of an equivalent length, as we discussed earlier, we can write W is equal to R bar q to the power beta. So, with respect to that we can change, say with respect to minor loss also we can add this, and then we can get a relationship between the discharge and losses. So, where R is the pipe resistance coefficient which we discussed earlier, and sigma k is corresponding to the minor losses. So, now and as far as say if there is a pump is involved in the network, so as we discussed earlier, we can have the pump head and discharge representation or discharge relationship. So, generally this will be given by the pump manufacturer, and so the general form of the equation will be HPQ is equal to A0 plus A1Q plus A2Q square, where A0, A1 and A2 are the non coefficients. So, this can be written, the pump head and discharge can be represented as a function of Q, and then also if with respect to actual power utilized, we can write HPQ is equal to Wf by gamma q, where Wf is the actual power, q is the discharge through the pump, and then say gamma is the specific weight of the fluid which is pumped. So, these relationships also we can utilize with respect to the generalized relationship which we have seen here. That means here equation number, this equation continuity equation, and then the energy balance equation, and then if there is pump involved in the network, then with respect to that change is to be added this equation, and then say we can use with respect to additional necessary formulation relation between discharge and loss, we can use this equation number 12. So, now by utilizing, we can say when we go through all these equations, we can see that the equations of the energy balance or the mass balance, these equations we can see that it is non-linear in nature. So, to solve these non-linear equations, we have to generally go for iterative solutions. So, it will be much easier if we can linearize these energy equations, so that the solution will be much easier. So, we will now briefly discuss how to linearize these energy equations. So, here this equation 10 which we have seen here, this equation 10 which we have seen here is a general relation which can be applied to any path or closed loop in a network. So, if it is applied to a closed loop, then delta H is set equal to 0. So, here this equation delta H is set equal to 0 if it is a closed loop, and then if it is applied to a closed loop, delta H is set to 0, and if no pump exists in the path or loop, the HPI is equal to 0. And equation 9 can be considered to be a subset of equation 10. So, here this equation number 9, so this is actually a subset of equation number 10 as we have seen here. So, now this with respect to the network which we consider. So, our aim is, since this non-linear equations generally it is difficult to solve. So, we are just here discussing the possibility of linearizing it. So, in the equation number 10, say we are using the loop or path in the network. So, if you define the function f q to contain the nonlinear terms w q and h p q in the formula. So, if you represent this function, if you define a function phi q to contain the nonlinear terms the w q and h p q, then we can write phi q is equal to w q minus h p q is equal to r bar q to the power beta minus h p q as in equation number 16. So, now this equation 16 can be expanded in a Taylor series. So, that we can write phi q is equal to phi q 0, phi as a function of q 0 plus d phi by dq into q minus q 0 plus d square phi by dq square into q minus q 0 all square by 2. So, as in this equation number 17, this is obtained from the Taylor series. So, here this you can see that this q 0 is an estimate of q, and to approximate phi q accurately, q 0 should be chosen. So, that difference q minus q 0 is numerically small. So, what we are doing here, this equation, say we are trying to represent the nonlinear equation, we define a function phi q with respect to the nonlinear terms w q and h p q as in equation number 10 we discussed. So, then we are using the Taylor series. So, if we use the Taylor series by retaining the first two terms on the right hand side of equation 17 and using equation 16, we can have phi q is equal to r bar q 0 to the power beta minus h p q 0 plus beta r bar q 0 to the power beta minus 1 minus dHp by dq all into q minus q 0 as given in equation number 18. So, here this approximation of to phi q is now linear with respect to q. So, this we achieved through by using this Taylor series and only using this first two terms. This will be continued as in this equation number 17, we use only first two terms here. So, by retaining the first two terms on the right hand side of equation 17 here, we get phi q is equal to r bar q 0 to the power beta minus h p function of q 0 plus beta r bar q 0 to the power beta minus 1 minus dHp by dq into q minus q 0. So, now let us introduce here a parameter sigma is equal to beta r bar into q 0 to the power beta minus 1 minus dHp by dq from this as in this equation number 19. So, if we introduce this, we can write say using equation 14, that means here this equation 14 here and this equation 14 here with respect to the pump equation. So, if we use that equation here, we can write with respect to the pump head, we can write sigma is equal to beta r bar q 0 to the power beta minus 1 minus a 1 plus 2a 2 q 0 as in equation number 20. And alternatively, this equation number 15 here, which we have seen this relationship 15 here, 15 is that means with respect to the actual power used, that is given by this equation 15, we can write here, say we can transform this equation into b sigma is equal to beta r bar q 0 to the power beta minus 1 plus w f by gamma q 0 square as in equation number 21. So, finally, if we substitute 19, that means this equation and this for sigma into 18, we get phi q is equal to r bar q 0 to the power beta minus h p into q 0 plus q minus q 0 sigma is equal to w 0 minus h p 0 plus q minus q 0 into sigma as in equation number 22. So, where w 0 is w q 0 w as a function of q 0 and h p 0 is a function of q 0 as h p q 0 here. And finally, this equation 22 is substituted into the former equation 10 to produce the linearized loop or path energy equation as plus or minus sigma plus or minus I w 0 I minus h p 0 I plus sigma q I minus q 0 I into sigma I plus delta h is equal to 0. So, here you can see that this beta is generally used as 2. So, we finally get the equation 22 as a linear equation, and finally, after substituting this equation 22 into our earlier equation, the energy equation 10, we get as the equation 23, which can be the general form of the equation which we can utilize for the solution of the pipe flow networks. So, so far what we have seen, we have derived the equations, generalized equation for say energy equations for with respect to various pipe nodes or with respect to various pipes as we have seen, and then we have seen the generalized equation of continuity or continuity balance we have seen, and so these are the generalized equation which we use for the pipe network analysis. And say these equations, the energy equation is nonlinear in nature. So, what we have discussed just now is how we can linearize this equation and we can make it the equations linear, and then we can go for the solutions. So, like this we can write the general form of the say for any kind of pipe network, we can derive the generalized equations with respect to the continuity balance and with respect to the energy, and then we can solve these equations for the unknown discharges or the heads at various node or other various locations. So, now we have seen the generalized equation. Now, next question is how to solve these equations. So, here say in literature we can see different types of analysis of pipe network. So, here we will discuss few of the important types of analysis. with respect to the generalized equation we have seen earlier. So, in literature we can see 4 types of analysis. Say this different types of analysis which we can see in literature is based upon whether it is static or dynamic. That means the analysis which we are carrying out is with respect to whether it is varying with respect to time or not varying with respect to time. So, if it is not varying with respect to time, we say that kind of analysis is static, and if the time variation also included in the analysis, then we say that that kind of analysis as dynamic analysis. And then say whether we analyze with respect to the nodal heads. We have seen that in the pipe network we have number of nodes, number of pipes are connected and junctions are there, and there are also loops are there. So, the analysis which we do, whether it is with respect to the nodal heads, then say that will be one type of analysis, and whether if you are doing the analysis with respect to the flow through each pipe junction, then with respect to this, whether we are going for static analysis or dynamic analysis, or we go for nodal head analysis or nodal flow analysis, generally we can have 4 types of analysis, pipe network analysis. So, first one is static node head analysis, second one is dynamic node head analysis, and then third one is static node flow analysis, and fourth one is dynamic node flow analysis. So, we will briefly discuss these different types of analysis now here. So, first one is the static node head analysis. So, here we find the behavior with the fixed and non-hydraulic gradient line values at reservoirs and demands completely satisfied, such that we calculate the supplies from the source nodes and available HGL values at each nodes. So, in the static node head analysis, our aim is to find the behavior with respect to the already known HGL or hydraulic gradient line and the fixed nodes, and then we assume that all the demands are completely satisfied, and then we calculate the nodal heads with respect to say the supply, the available supply, and then the source nodes. So, here in the static node head analysis, there are different types of models available. This actually most of the water supply pipes lines, most of the analysis generally we will be doing this static node head analysis. It is much simpler compared to the other 3 types of analysis which we discussed earlier. So, the static node head analysis is one of the most commonly used analysis for pipe network. So, there are number of models available, few of the models are described here. So, one of the most commonly used static node head analysis called the Hardy-Cross method, which will be discussed later in detail. We will be discussing the Hardy-Cross method in detail later. So, this different types of analysis with respect to pipe networks you can see in the textbook Optimal Design of Water Distribution Networks by P.R. Bhave, published by Narosa Publishers in 2003. And then as I mentioned, there are different types of static node head analysis. First one is the Hardy-Cross method, which we will be discussing later, and second type of analysis is called the Newton-Raphson method. So, in the Hardy-Cross method, generally we consider say one loop at a time, and then we will be trying to do the successive approximation which we discussed earlier. But in the Newton-Raphson method, what we do, we consider all loops or all nodes simultaneously, and we do iterations until we get a stabilized value, so that between the iterations the convergence is achieved. So, the Hardy-Cross method is a simplified form of the method of successive approximation, but the Newton-Raphson method we consider all the loops or all the nodes simultaneously, and we do iterations such that and then we get a stabilized solution. The advantage of Newton-Raphson method is that we will be getting faster convergence. And then other methodologies in the static node head analysis include linear theory method, which we discussed earlier based upon the equations which we have discussed earlier in terms of either discharge Q or H equations, and then fourth method generally used is called gradient method. So, with respect to the flow gradient, we will be calculating the various unknown. So, like this number of methodologies are available with respect to this static node head analysis. Those who are interested, they can refer to the textbook by Professor Bhave. And then the second type of analysis which we want to discuss briefly here is dynamic node head analysis. So, as I mentioned, in the dynamic node head analysis, so we will be say looking for the heads at different points of time. So, this it is the analysis with respect to time. So, at various times level or with respect to various time intervals, we will be calculating the nodal heads at various nodes. So, this analysis here you can see that it is with respect to time. There are different methodologies also for dynamic node head analysis. So, it involves methods like direct procedure, that means by head discharge relationship, there we can have a head discharge relationship, and also there are methodologies like iterative procedure. So, here again, as we discussed earlier, the solution is obtained through iteration. So, those who are interested more details about these methodologies, they can refer to the book by Bhave. And then say we have seen this say these two dynamic node head or static node head analysis. So, here we are taking the heads at various nodes and trying to solve for that on the assumption that all the flow demands are met at all the nodes. So, based upon that assumption only we do the nodal head analysis. But this node flow analysis, in the node flow analysis, depending upon the demands, say all the demands may not be satisfied at some nodes. So, that there can be deficient conditions. So, that we have to determine the available nodal flows. So, that is the difference between nodal head analysis and nodal flow analysis. So, for node flow analysis, this assumption of that all the demands are satisfied are not used. So, demands may or may not be satisfied. So, at some nodes, if the demands are not satisfied, there can be deficient conditions. So, with respect to this deficient conditions only, say we will be trying to solve the problem. So, we have to determine the available nodal flows at say at various locations, at various junctions. So, here also with respect to node flow analysis also we can have the static or dynamic conditions. So, the third methodology, the third type of analysis is called static node flow analysis. So, in the static node flow analysis, we predict the performance of deficient network at a particular point of time. So, here the deficient conditions are also considered, and then we try to predict the performance of the deficient network at that particular point of time. And in a very similar way for dynamic node flow analysis, we are trying to predict the performance of a deficient network over a certain interval of time, and then at various intervals of time we can find the flows through various nodes with respect to deficient conditions. So, these other methodologies like static node flow analysis, dynamic node flow analysis are also discussed in detail in the book by Professor Bhave. So, those who are interested, they can refer to this textbook. So, now here we will now discuss. So, the earlier, as I mentioned, one of the most commonly used type of pipe network analysis, static node head analysis, and so here we will discuss now in detail about this Hardy-Cross method, which is very commonly used for the pipe network analysis. So, in this Hardy-Cross method, actually this method has been developed in 1930s. So, Hardy-Cross 1936 introduced this method to solve the simple pipe networks. So, this method is also, as we have seen the generalized equation, this Hardy-Cross method is also based upon the generalized network equations which we have seen earlier. So, this method is also known as single path adjustment method. So, here we consider if there are number of network in a network, number of loops may be there, number of paths may be there, but in the Hardy-Cross method we consider a single path at a time and then or single loop at a time, and then we adjust the flow within that loop. So, this Hardy-Cross method is also known as single path adjustment method, and Hardy-Cross method is easier and it takes less time in solving pipe networks, since at a time we are dealing only single path. So, this is much easier, and depending upon the problem we can easily solve the network problem. And here the Hardy-Cross method, the flow rate in each pipe is adjusted iteratively to achieve the solution. So, here this Hardy-Cross method also we utilize, we use the we assume the flows through the network which we consider, and then the flow rate in each pipe is adjusted iteratively, and then we achieve the solution. So, here this Hardy-Cross method is based upon the following laws. Here if you consider a network like this, and here you can see a part of the network is shown with respect to various pipes, and here two nodes are there. So, the Hardy-Cross method is based upon the assumption that the sum of pipe flows into and out of a node equals the flow entering or leaving the system through the node. So, here the basic law, that means this is with respect to the continuity. So, here the sum of pipe flows into and out of a node equals the flow entering or leaving the system. So, whatever coming from the, say, if you the flow coming this direction or that direction, then that should balance with respect to the flow going out of the node. So, based upon this law only this Hardy-Cross method is working, and also the hydraulic head at a node is the same at upstream or downstream of the node. So, if you consider this as the node, then whether upstream, that means here or here, the hydraulic head is same. So, based upon these assumptions or these basic laws only, say actually these are fundamental laws with respect to the continuity. So, the Hardy-Cross method is based upon these two basic laws. And then in the Hardy-Cross method, as we discussed, it is a simplified version of method of successive approximation. So, we have seen that the basic equations, the generalized equations, this generalized equation we can solve through successive approximation. Actually, Hardy-Cross method is also type of the method of successive approximation, but it is applied to a set of linearized equation, so that there is no inversion of matrix involved. So, here we use the linearized form of the equations which we discussed earlier, and the continuity relation is decoupled from the solution of energy relations, and then also we can superpose the type of solution which we do with respect to the loop which we do, and only the problem here is the convergence may not be so faster, since compared to the Newton-Raphson method, as we discussed, the Newton-Raphson method we consider all the loops or all the nodes at a time, but in the Hardy-Cross method we use only one loop at a time. So, the convergence may not be faster compared to the Newton-Raphson method. So, now we will discuss here the various steps involved in the Hardy-Cross method. So, here say first we assume for the given network we will put the node numbers, and then we will identify the fixed grade nodes, and then also we can identify the which are the loops. So, the Hardy-Cross method steps include first the number of loops of the pipe network we can identify, and then step number 2 we can assume a flow direction. So, generally the consider clockwise flow direction as positive and counterclockwise flow direction as negative, and then step number 3 is assume an initial flow through each pipe. So, for the given network we assume a flow direction. So, since we do not know which direction the flow is going, so we assume a flow direction, and then also we assume some initial flow through each pipe. So, then after these assumptions for the given network we can consider each loop, and so for the given loop we can calculate the head loss for each pipe using the formula HF is equal to gamma R, HF is equal to R q to the power n, where R is a function of the fluid flowing through the pipe and pipe material. So, HF is equal to R into q to the power n, that is equal to so this generally we write as R into q into modulus of q to the power n minus 1. So, this is generally represented to take care of the direction which is discussed here. We write this HF is equal to R into q to the power n minus 1. So, now here in this with respect to the steps we have considered here, the total head loss across a loop should be 0 in case of a correct distribution of flow. So, what we did is we for the given network we assumed the flow direction, and then also we assumed the flow through each pipe. So if our assumption is right, then so for the given loop the head loss should be 0 as per the basic assumption which we use in this analysis. So if the distribution is not right, then there will be some error, so that we have to check and then we have to redistribute. And then also the losses in clockwise direction is positive and counterclockwise we consider as negative, and here this R, which we consider HF is equal to R into q to the power n, this equation, this R is a constant for each pipe which depends upon the fluid and pipe properties, so that we can either find out or it will be given for the given network. So we assume that this R value is known for the given pipe network. And also in this equation this n is a constant. So here this n is, when we assume that flow is fully turbulent and pipe is rough, this n is equal to 2, generally n is equal to 2, and when for smooth pipe it will be generally less than 2, it may be 1.8 something like that, depending upon the type of pipe and the other fluid properties. So for turbulent rough pipe n is equal to 2, and then here say as we discussed, we assumed the direction and also we assumed the initial flow. So since the assumption may not be right, so due to that say there will be a correction will be there, so that we can find out this correction and then we can adjust the flow in each loop by corrective discharge delta q. So then in each loop, to balance the head loss, as we discussed this sigma, so with respect to each pipe we can write sigma r into q to the power n is equal to 0. So to find delta q we can write this q is equal to the initially assumed value plus delta q, q is equal to q 0 plus delta q. So that HF is equal to r into q to the power n, so that is equal to r into q 0 plus delta q to the power n, so that is equal to r into q 0 to the power n plus n into q 0 to the power n minus 1 delta q plus etc. So if you consider only first two terms, then if delta q is small and all terms after second can be dropped, then for the given loop or for the given circuit we can write sigma HF is equal to sigma r into q into modulus q to the power n minus 1, that is equal to sigma r q 0 modulus q 0 to the power n minus 1 plus delta q sigma r n modulus q to the q 0 to the power n minus 1. So this should be equal to 0. So from which we can get this discrepancy in flow, that means delta q we can obtain from this equation, delta q is equal to minus sigma r q 0 into modulus q 0 to the power n minus 1 divided by sigma r n q modulus q 0 to the power n minus 1. So using this equation we can get delta q and then we can adjust with respect to this delta q which is discussed in the next step. So with respect to here we have seen we are calculating the head loss for each pipe, and then for we can also calculate the quantity Rn into q to the modulus q to the power n minus 1, which we discussed in the earlier equation. Now for each loop this delta q is calculated. How we got this delta q is derived here. So this delta q is calculated, so that is equal to minus sigma j is equal to 1 to m into r q 0 into q 0 to the power n minus 1 divided by j is equal to 1 to m r n modulus q 0 to the power n minus 1, where here we can take n as 2 unless it is not mentioned, and m is the number of pipes in a particular loop. So j is equal to 1 to m, and here also j is equal to 1 to m. So once we get this correction delta q, then we can apply in next step the correction delta q is applied to each pipe in a loop, and then this procedure is continued. We can continue for all the loops, and then finally we can check whether sigma r into q to the power n is equal to 0 or not for the given loop, and then we will continue this. Generally, since we have started with an assumed value of delta q, the flow through each pipe. So this relationship this sigma r into q to the power n will not be 0 generally. So until we can put a convergence limit, a desired limit like 0.0001 something like that, or if you want exact 0, a number of iterations will be required. So, otherwise we can put a limit, and then depending upon that we can find out the flow distribution through each pipe. So, this iteration is done till delta q is very small, and then say we can find out the flow distribution through each pipe. So, all these steps we can utilize in this various cases, same depending upon the network. So, these are the fundamental steps used in the Hardy-Cross method. So, to demonstrate this Hardy-Cross method, we will just solve one simple example with a pipe network of including two loops. So, here we solve the pipe network shown here in this slide. So, in this pipe network there are two loops, and the flow is coming this direction 10 cubic meter per second, and for various pipes the R values are given, and also there is an outflow at this node C 4 cubic meter per second, and an outflow at node F 2 cubic meter per second, and outflow at node E 4 cubic meter per second. So, here our problem is we want to find out the flow through each pipe with respect to this inflow here. So, here the pipe junctions or pipe nodes we can identify A, B, C, D, E and F, and number of pipes here 1, 2, 3, 4, 5, 6, 7. So, we have 7 pipes, and then we have say here 6 nodes for this given problem, and then 1 inflow to the system, and then 3 outflows from the system. So, we want to find out the flow distribution in each pipe for this given network. So, as we discussed earlier, the solution. So, here we can see that there are 2 loops in this network. We assume the flow direction like this. So, here the flow direction A to B, B to C, and A to D, D to E, and B to E, and E to F, and then F to C. Like this we assume the flow initially, and then we will assume some initial flow also. So, step by step solutions which we discussed earlier for the Hardy-Cross method we will use here. So, here already the R values are given. So, we assume this with respect to the inflow is 10 here. So, we assume 5 flows through AD, the pipe AD, and 5 QMX flow through pipe AB, and then B to E 2 QMX, and D to E 5 QMX, and E to F 3 cubic meter per second, and B to C 3 cubic meter per second, and F to C 1 cubic meter per second. So, these are our initial assumed value flow through each pipe. So, now we will apply Hardy-Cross to see that, and this we get the correct value. So, these are only assumed value. So, now we will proceed with respect to the iterative procedure which we have discussed earlier, and then step by step we will do the calculations here by using the Hardy-Cross method. So, this shown in this table. So, first we consider the loop 1, this is loop 1 and this is second loop. So, for the loop 1 for pipe AB, BE, ED, DA, R values are 1, 2, 3, 3, and then QJ the assumed flow is 5 QMX, 2 QMX, and minus 5. So, here this direction, if it is clockwise it will be positive, if it is anti-clockwise it will be negative. So, that is why this plus and minus, and then we find this RQJ modulus QJ, and then we find here we assume that in this equation n is equal to 2, since no other special values are given, we assume n is equal to 2. So, with respect to that we write 2R modulus QJ. So, for each various values we can now do the calculation, and then we can sum it up all this for the given loop. So, the summation will give minus 117, and then the summation of this values will give 78. So, this delta q now we can find out. So, delta q we use this equation here, and delta q is by using this equation for all the pipes. So, we will get this delta q as 1.5. So, we will correct the assumed value of the flow by using this 1.5. So, it will be we can add 5 plus 1.5 6.5. In the iteration number 1 we get 6.5 for AB, pipe AB, and pipe BE it is 2 plus 1.5 3.5, and pipe ED it is minus 5 plus 1.5 it is minus 3.5, and pipe DA it will be minus 5 plus 1.5 minus 3.5. So, similar way we can do for loop number 2, iteration number 1. So, loop number 2 you can see this is loop number 2, it includes BC, CF, EF and BE. So, this for pipes. So, BE already we have calculated. So, same values we will use, we will put it from here. So, the assumed values here, say R values are given us for BC as 10, CF 5 and FE is 3 and EB is 2 and QJ the assumed value is 3 and CF it is minus 1, FE it is minus 3, BE we have already calculated. So, that we can write this now as minus 3.5 with respect to the direction in this particular loop. So, that now we will find out RQJ modulus QJ, 2RQJ modulus 2R modulus QJ and then we will sum it up. So, we will get 33.5 here 102 in this column and then we will find out delta Q, we will get here delta Q as minus 0.33 and then we will correct. So, the correction will be 3 minus 0.33 for pipe BC, it will be 2.67 and for pipe CF it is minus 1 minus 0.33, it will be minus 1.33 and pipe FE it is minus 3 minus 0.33, so minus 3.33. So, similarly EB it will be minus 3.83. So, now the first iteration is over for loop 1 and loop 2 and then we will go for the second iteration for loop 1. So, similarly say now we have already the corrected values here and also this B is considered this the new value for the loop number 2 will be using. So, all this value will substitute here in this iteration number 2 and then we will find out this RQJ modulus QJ, 2RQJ and then we will sum it up and then we will find out delta Q as we discussed earlier. So, here in this iteration we will get a small value. Now, the solution is improved, it will be 0.03. So, then again we will correct the flow through each pipe for the loop 1. It will be now 6.53, 3.86, minus 3.47 and minus 3.47 and then now iteration number 2 for loop number 2. So, similarly what we did for BC, CF, FE and EB. So, QJ is already obtained from the earlier and here again this B is 3.86, that is now minus 3.86 in this loop and we can find out RQJ modulus QJ, 2RQJ and we can sum it up. So, here it will be minus 0.6, it will be 102.12 here and we can find out delta Q which will be 0.01 approximately. So, here now the corrected value with respect to this we can correct. So, it will be here 2.68 minus 1.38 minus 3.32 and minus 3.85. So, with this iteration number 2 is over. So, now we will go to iteration number 3. So, for iteration number 3 again from the iteration number 2 the corrected QJ is used. So, these are the corrected QJ 6.53 through pipe AB, pipe BE 3.85 obtained from here and then pipe UD minus 3.47, pipe DA minus 3.47 and then very similar way we can find out RQJ modulus QJ and 2RQJ and sum it up. So, it will be here RQJ QJ will be 0.05 and then 2RQJ we can find out 70 point total will be summation will be 70.13. So, this will be almost equal to 0, it is same we can see that it will be 0.00 something. So, it will be you can take it almost it is converged. So, the corrected QJ will be 6.53, 3.85 same value minus 3.47 minus 3.47 and then iteration 3 for loop number 2 say 2.68 minus 1.32 and minus 1.32 3.8 minus 3.385 from here and so and this here we will be writing RQJ modulus QJ 2RQJ and then sum it up. So, this we can get the delta Q. So, here also it is almost 0, it will be 0.00 something. So, if you take only up to the desired accuracy, so then we can now get the corrected value as 2.68 minus 1.32 minus 3.32 and minus 3.85. So, now in the second iteration we have almost reached the solution. So, if further accuracy is required we can continue the solution or we can take this as the solution. So, here now finally we can write all the flow through all pipes like this. So, that we can see that all the mass balance is achieved or continuity is achieved and then like this we can get the solution. So, like this say this Hardy-Cross method, this is one of the easiest method for pipe network analysis. So, this is actually it is we are using the generalized equation method of successive approximation, and then we are considering one loop at a time, and then we are iterating to get a solution. So, this is one of the most commonly used method. Also, we can use methods like Newton-Raphson method, or we can use numerical methods like finite element or finite difference methods, depending upon the solution which we are looking for, or if we are having some packages, software packages, we can use directly to find out the solution. The Hardy-Cross method, we considered the static node head analysis. So, like that, if you are looking for dynamic node head analysis or static node flow analysis, dynamic node flow analysis, we can do the analysis and then we can solve the pipe network flow problems. So, now with this we have finished the pipe networks flows and also the various aspects with respect to the multiple pipe flow system. So, now as the last topic in this video course, we will now consider the unsteady flow in pipes or unsteady flow in closed conduits. So, we have seen earlier when we discussed the different types of flow earlier, we have seen that the flow can be steady state or unsteady state, depending upon whether there is the various flow parameters are changing with respect to time or not changing. It can be unsteady or steady, and also we can have the flow as uniform or non-uniform flow. The flow parameters are same throughout from one distance to another. So, then it will be uniform, and if it is changing with respect to distance, it will be non-uniform flow. So, now with respect to the pipes or with respect to closed conduits, we will briefly discuss the unsteady flow and its governing equations and various aspects with respect to the unsteady flow. So, the unsteady flow, as we have discussed earlier, the flow conditions such as velocity and discharges change with respect to time, and also sometimes this flow is said to be transient state flow. So, generally say transient state flow also sometimes used as unsteady flow, but in transient state flow we take it in such a way that the flow conditions changes from one steady state to another steady state condition. So, actually this time dependent flow we can consider in such a way that at a particular time this is a steady state, and then next another steady state, like that. So, that way when we consider the flow, we say it is transient state flow, and similar way we can have uniflow and non-uniform flow. And also depending upon the flow, we can say the flow to be steady, oscillatory or periodic flow. So, when flow conditions are varying with the time and repeating after a fixed time interval, then we say that kind of flow as steady, oscillatory or periodic flow. So, here what happens is the flow conditions are varying with the time, but it is repeating after a fixed time interval, say few seconds or few minutes after that the flow conditions are repeating. And so, here we have a fixed time interval, that is called the period. So, for the steady oscillator periodic flow we have a fixed time interval, so which is called period, and then this which is represented generally as t, and we can find out the frequency of oscillation. So, we can see that the flow is, say for example, when we consider the flow coming from a reservoir like this, and then if we are having a pipe connected from the reservoir, and here there is a flow, and here if we have a valve, and then we can see that if you operate this valve, so with respect to this, say whenever we close the valve, then we can see that oscillations are taking place, and then we can see that this is also say periodically or steady oscillatory flow. So, with respect to this, if the fixed time interval is the period, and then we can find out the frequency of oscillation, the flow is going from one place to another. So, with respect to that we can find out the frequency of oscillations. So, the frequency of oscillation is f is equal to 1 by t, where t is the period of the flow, and then this frequency can be represented as in radians per second, then it is called a circular frequency. So frequency can be either in terms of cycles or it can be in terms of radians per second. So when it represents terms of radians per second, we call it as circular frequency. And when we deal with this unsteady flow conditions, as we discussed here, one of the common phenomena is column separation. So if pressure in the pipeline drops below the vapor pressure, then we can see that cavities are formed, and then we can see that liquid columns may separate. So depending upon the conditions in the pipe, if depending upon the pipe length or the pressure in the pipeline, there can be conditions such that the pressure in the pipeline may drop below the vapor pressure, then we say that cavities are formed and liquid column may separate. So with respect to this, we can define a term called water hammer. If we are using with respect to water, then we will call it as water hammer, or with respect to oil, or if it is with respect to steam, we will call it as steam hammer or oil hammer. So now say this water hammer is the pressure fluctuations caused by a flow change, or sometimes it is called a hydraulic transient. So the water hammer is the pressure fluctuations caused by a flow change. If there is a flow change, if there is a sudden closure of a valve, then with respect to that there will be a flow change, and then pressure fluctuates within the pipe. So that kind of pressure fluctuations are generally termed as water hammer, and then this water hammer is also called as hydraulic transients. So here you can see that with respect to this figure, so whenever here there is a reservoir and there is a pipe, and then if we close this valve, then we can see that a wavefront will be moving this direction, and then it will reach the reservoir, and then it will go back again to this direction. So like that there will be say pressure fluctuations with respect to this flow change, so which is called a water hammer. So with respect to this water hammer and then the unsteady flow equations, we will discuss in detail in the next lecture. So more details we can also see the textbook by Hanif Chowdhury, Applied Hydraulic Transients. So we will be discussing more about the water hammer aspects and the hydraulic transients and unsteady flow equations in the next lecture.